So far, we've covered a couple different ways to create and use callable objects. In this video, let's round out this week's discussion by taking a look at two ways to store generic callables. A lot of the code we work with in ROS uses callbacks, functions we give to ROS which it should call when some new data is available. How do these ROS objects actually hold on to the callbacks we give them? Well, that's exactly what we'll talk about today. One way to store a reference to a function is through a function pointer. This is something C++ inherited from the C programming language. A function pointer is a special kind of pointer that points to a function instead of an object. It can be called like a function, and that call directly calls the target function. When we've been passing function names into std-bind, we've actually been handing over function pointers. The syntax for declaring a function pointer variable can be a little confusing at first, because it's unlike just about any other variable declaration syntax. A function pointer needs to know what parameters and return type are expected of the target function, so that information has to be captured in the type. Thus, function pointer types look a lot like the function signature. A function pointer declaration looks like this. The name of the variable is in the middle, surrounded by parentheses and with an asterisk in front of it. Then to the left of that, we've got the return type of the target function, and to the right is the parameter list of the target function. By looking at this declaration, we can see the return type and parameters that our target function will need to adhere to. Here's a quick example of using a function pointer to store a callback. We've got a class called worker that's going to do some task for us and call a callback when the result is ready. It's got a private variable that stores a function pointer to the callback that we initialize in the constructor. Inside of our doWork function, we call the callback member variable, which actually calls the target function we were given in the constructor. In the main function, we create a new worker using a lambda we created there as our callback. When we call doWork, the class calls our lambda callback and the result is printed. An important thing about function pointers is they can only point to freestanding functions and captureless lambdas. Because function pointers don't point to objects, they can't deal with bound functions, callable objects, or lambdas that have captures. The other way to store callables we'll talk about today is using std function. This is a generic type we can use to store any callable object or function. Just like function pointers, std function needs to know the signature of the target function it will hold. It takes that information in through a template argument. When declaring a std function variable, we template it with the return type and parameter list. Std function objects are able to store any callable. You can set the target to a freestanding function, a lambda with or without captures, a bound function, and more. Here's the same worker example we saw earlier. This time, we're using a std function to store the callback instead of a function pointer. Note that we've included the functional header as this declares the std function type. In the worker class, we're using std function objects instead of function pointers. And down in the main function, we're now able to use captures in our callback lambda. The same general flow as the previous example happens here. We pass in the callback through the constructor and store it into this private member variable. Then, when we call doWork, it calls our callback function variable, which in turn triggers our lambda. The only difference is now that our lambda includes a capture, it does a little math of its own before printing the value to the console. And that's all for this week. We've taken a look at operator overloading, callable objects, lambdas, and storing function references in variables. For now, it's most important that you're able to recognize these patterns when reading code, and understand how to give functions to library objects that use these tools.